Hello everyone, and welcome to Global Summit. My name is Benjamin Debo, and I'll walk you through what horizontal scalability means on InterSystems IRIS. So I'll give you a tour of the various dimensions across which we can scale, and hope that this sets you on a path to scale up your business and scale up your data and compute. So this is a very important topic, because there's a world out there where data can get really big and iron doesn't grow on trees, so the iron might not be able to grow along with that data. So some of you may recognize this picture. Anybody who does recognize this? There. It is a library. You might think you recognize it from a movie, but it's actually not from a movie. This is one of the beautiful offices on Epic's campus. So InterSystems is one of our partners who has a sprawling campus in Wisconsin, and who has kind of themed every one of their buildings according to a particular nice, fantasy or non-fantasy theme. Anyway, so I thought they're always the ones that present us with the biggest scalability challenges that we ever hear about. So I thought it was worthwhile to start with something that's themed along with them. So let's think about a scenario where we are a lore master. We live in a beautiful castle, maybe in Wisconsin, and we have a library full of magical books, with books that people from all over the world, from all over the Middle Earth, whatever, come up to us, and they ask questions. They want to know something that is in one of our magical books. So they want to read from those books. Sometimes they might bring additional books. They might contribute some additional knowledge. Sometimes they might steal something. And it's getting really tiring to answer all of these people. So you want to kind of outsource that to technology. And technology in the fantasy world doesn't exist. So you post a job advert on the local market, and then a gnome walks up and he says, I want to do that for a couple of bronze coins. So you've got a gnome that manages your library. So people can ask questions to this gnome. He runs and finds the right book and then answers the question. So that's great. Now imagine that you've cast a economical spell, and more people are showing up, and there's a big queue across the moat. Lots of people asking questions, and your gnome just can't handle it. So there's no worker unions in this world, so you can just fire the gnome and replace him with an elf. Elves are smarter, stronger, and they can just handle bigger libraries. They can handle more questions. They can allow you to scale up. And if one fine day you're really successful and you keep on getting more people showing up on your doorstep, you can still fire the elf and hire a troll, and the troll can handle an even bigger workload, and so on. And maybe there's still dragons out there, but I guess dragons are very expensive. The problem with this model is that in this world, we have worker unions, or we also have kind of a limited amount of money that we can spend. So that vertical approach is kind of costly. You need to, you can't make use of the elf after you fired him. In the same way, if you kind of scale up to bigger hardware, you might not necessarily be able to recover any of those investments. So it is extremely important that you are good at capacity planning. And Epic is terrific at capacity planning because they have tremendous knowledge of their platform and the needs of their platform, and they can really predict with very fine granularity what kind of hardware would be suitable. Our technology architect team is also extremely skilled at helping you make those decisions for the health share. Sorry, do you have a question?
Not a question. In vertical scalability, you have always downtime, right?
With vertical scalability, you have yes, but there is. So it's a really good question, because it allows me to make a little promotion for the developer community. If you look for vertical scalability, I believe you should find an article from Bob Binstock, one of our esteemed documentation writers, that details exactly how you can get minimal downtime vertical scale-up recipes in the cloud. So where it walks you through the steps of upgrading your, GP3 whatever X large to a 4X large instance on AWS in one quick step. So even though the cloud makes it slightly easier, capacity planning is extremely important, and it is an art that you need to master, and that many of our partners have mastered, and that we can definitely help with. But it is one of the biggest challenges with the vertical scalability model, obviously next to the cost of dragons. Yes. If you have a question, feel free to walk up to the microphone and ask it there. So that's vertical scalability. There's also an alternative. So rather than trying to find trolls, trying to find elves, you can also just hire more gnomes and let the gnomes work together. And those you can just have a bunch of gnomes that are at the ready. If you have more people coming in that ask questions, you can have those gnomes run all around your library, fetch the books, answer the questions. So that is horizontal scalability, and it is also easier to quickly hire more gnomes. They're easier to get by, I guess, and they're also easier to get rid of. You can easily elastically scale in and out if you want to. So that's a big advantage of horizontal scalability. But the complexity here is, how are you going to distribute the work? How are you going to make sure that all the gnomes are reasonably happy, and especially that your users are happy and are being served in an efficient manner, and that data and work is being distributed evenly? So this is a very different type of problem. So this is not a problem that is kind of upfront planning and some operations. This is really the core of your system that needs to handle horizontal scalability. And that's why I'm talking about it today, to walk you through how InterSystems IRIS addresses horizontal scalability. So with that not so fantasy intro, let me walk you through how our architecture looks for these various kinds of, or for various types of horizontal scalability. And then we'll talk a little more about the specific capabilities that we've added over the past couple of releases, because there's been quite a bit of evolution in this area. And then at the end, I'll end with a couple of examples of customer deployments and an outlook on what we're up to. Okay, so I'll talk to you about this fantasy library where we're trying to use gnomes. And as I mentioned, we're going to talk about horizontal scalability. So we're hiring more gnomes. And if your library remains more or less the same in terms of size, you only need more gnomes that run around and answer requests from visiting scholars and wizard apprentices. So you have just one gnome that remains in the library and knows where all the books are, and all the other ones that focus on just the running. So that is compute gnomes, runner gnomes, and then one data gnome that stays in the library and knows where to find everything. So that is what horizontally scaling the compute axis means. And on InterSystems, we don't use gnomes for it. We use the enterprise cache protocol for it. We've got many customers around the world that have been relying on enterprise cache protocol for meeting the toughest scalability requirements. For example, Epic, one of Epic's bigger deployments, is serving up 88 million global references a second through a 23 node cluster in total. It is really a magnificent system, and that is serving up to 40,000 concurrent power users on Epic. So that is really cool. So from the user perspective and also from the application perspective, this looks the same. It doesn't really matter where the application is running. So it's totally transparent for an application. So an application might be running on the data node, but the exact same application could also be running on the compute node. And the application doesn't have to behave in a different way because we're presenting the same semantics in the compute layer as well as the data layer. And also, if you're having a client application that's not running on IRIS, but for example, something written in Java, it is also able to connect to any of the compute nodes or directly against the data nodes, and logically, it will see the exact same data in the exact same logical union form. It is something that within InterSystems we've grown accustomed to, but when we talk to analysts, they keep being amazed how smooth this is and how transparent this really is. Because if you look at other database vendors, they usually have a totally different technology that is responsible for this kind of caching. For example, for Oracle, it's times 10 or it could be from a totally different technology stack, like Redis deployed in front of your actual database. And that has an impact on your application. Your application doesn't talk to Redis the same way it would talk to, to the database underneath. Another great advantage is that it's fully elastic. You can spin up an additional compute node in a matter of seconds or less, depending on how fast the infrastructure can be provisioned. And you can also spin it down. It doesn't really matter. So I live in Belgium, and we don't really celebrate Thanksgiving, but our retail industry has turned Black Friday into a thing. And we have a nice customer in the electronics retail, Van den Borre, and they serve their web shop and inventory things. They have that all hosted on InterSystems IRIS. Now, the week before Black Friday, they just spin up a couple of additional ECP application servers in the cloud. They pay for them for the week until Black Friday. When all the promotions end, they spin them down. So they only pay for the infrastructure exactly when they need it. And that elasticity is really very cost effective for them. So I can just add a compute node and take it away if I need to. And then another great advantage or great thing that is very practical about ECP is that it's easy to organize. It is easy to organize your workload across these systems. For example, you could load balance your users on a couple of nodes here, and you could load balance some other workload, another category of users, perhaps on another node. This is also something that Epic uses. They have, for example, most of their compute nodes are used, obviously, to serve user workload, but some of the more data-intensive utility processes are now also running on ECP nodes, but separate from the ones used to serve the user applications, because they have different characteristics of how they interact with the data, and they would be competing for cache if they would be running on the same system. But this way, this segregating of workloads through compute nodes is a really practical and very simple approach. So that's scaling the compute access. Enterprise Cache Protocol has been around for many, many years, and we continue to innovate. Most of the innovations are driven by specific requirements from Epic and other big customers that are really at the upper end of the scale spectrum, because it already works so well at the middle end. So say that it's not just the audience grows, the number of people that show up at our castle that ask questions, but also the number of books. Say that there's an Amazon shop in Middle-earth, and that we've got Amazon Prime, and we keep ordering more books, and that they just don't fit on a single shelf anymore. And our Gnome that's in the library can't handle it all by himself. So we could replace the Gnome in the library, and we could use vertical scalability at that level. But there's also an alternative approach that might be more cost-effective if you're looking at hiring a dragon. So that is what we built sharding for. So sharding is about partitioning your data into shards, which can be physically located on different nodes to ensure that you're not constrained by other hardware. But it really doesn't matter. There's a lot of flexibility in that in those topologies. But the fact that your data is it doesn't show. Yeah, the fact that your data is spread across different nodes is, again, transparent to the users. When they connect to the system, they see the logical data as a whole. When they access the data through SQL or object models. And roughly speaking, there's kind of two main responsibilities for this sharding infrastructure. There is the transparent data management. So it means when you're getting the data in, that the data is transparently distributed across your instances. So that means both when you're ingesting individual records, but also when you're ingesting it in batch, that InterSystems IRIS will take care of making sure that the data is evenly distributed across the different nodes. So that's the data management part, getting the data in. For getting the data out, that's also where sharding has a role to play. If you're looking up an individual record, well, you might figure out on which node it is, or IRIS would figure that out. But also, if you're querying across your entire sharded table or your entire sharded extent, IRIS will take care of distributing your query to the different nodes and assembling all the data so that you're looking at one logical table, but getting the data that's physically located on many different nodes. So that's the micro and macro level of the query management. So that's our that's our scaling compute and scaling data capabilities on IRIS at a high architectural level. So I mentioned that for ECP, we continue to innovate on the high throughput, high end of the spectrum. For sharding, which was new in 2018.1 in the first release of InterSystems IRIS, we've actually done quite a bit more. There's been a lot of great advances from that first introduction. So I thought it was worthwhile to talk a little more about what we've been up to in those past years. So when we first released it, we started with SQL. SQL offers a nice kind of abstraction layer where both the ingestion and the query side offered hooks for us to make sure that the data distribution, the query distribution, the work distribution was taken care of properly. What we've done since that initial release is offering you a lot more flexibility on that. So we've made sure that we have full support for object access. So you can access individual objects, and you can also do something with those in a distributed manner, as you'll see on the next slide. So object access is now is something that actually many of our customers are using, are combining both object and SQL access in the same application, not least health share and track care. We've also introduced a lot of class level features. So we've added support for defining your sharded tables through a class definition in the first place, but also one-to-many relationships, the class hierarchy, functional indices. A lot of the things that were kind of limited in the first release are now fully available. Not to mention the ways how we offer the ability to define co-sharding relationships, so that tables who are often used together, the corresponding records are also stored together. And then support for stream fields. Maybe that doesn't sound as tricky as it actually was, but now those are also supported in the latest release. Well, actually already in the previous release. But so I mentioned that we offer object access. What we now in 22.2 also support is distributing object access. Is being able to distribute work across your cluster. So SQL is a non-procedural language. It's a query language. You define what you want, and then you let your database figure out how to actually get the data. You don't write something that fetches data from disk. That's what your database does. When you're working with a procedural language such as ObjectScript or Python, you do have to your code is running somewhere. And up till this release, it wasn't quite possible to distribute that kind of work without a little bit of manual work. So now what we have implemented is an API that's similar to the work queue manager that many of you will be familiar with, that allow you to kind of define a little piece of work in the form of a class method or in the form of a routine. And then you can broadcast that so that it gets executed on all of the nodes in your sharded cluster. You can refine that to not just all nodes, but only the compute nodes or only the data nodes. So this is great to, for example, kick off a load or do some routine transformation or maintenance work on all of the nodes. But you can also distribute work to all of the instances of a sharded class, all of the all of the rows in a sharded table. And that is very similar to the map command in a classic MapReduce paradigm, or the map function in JavaScript for that matter. So with this API method, you can distribute a piece of work to, for example, this method that gets executed for every record in your sharded class on the node where that record is physically located. So that is if you need to perform an operation on every row in a sharded extent, this is the way to go. So two simple methods that kind of give you the building blocks to distribute any kind of workload. Another thing that another thing that's very important why people would choose for horizontal scalability is the ability to scale out and scale back in, is elasticity. So that is something that we already offered early on because it's based on the ECP protocol for the compute tier. So you could already add compute nodes to your sharded cluster and then remove them when you no longer needed them. And that is obviously also a very smooth and instantaneous process. A couple of versions ago, we introduced the ability to also add nodes in the data tier. And now what we've introduced with 22.1 is the ability to rebalance your data without interrupting any operations. So, for example, if you've added a data node, new data would start flowing into all systems the very moment your data node comes online. But you might want to redistribute the existing data, the pre-existing data, across the different data nodes. Because when you're querying, your query result is only going to be returned after the last shard has done its work. So that's why you're always aiming for an even distribution of data. And now that distribution of data can happen completely online without interrupting your queries or ingestion. So that's a really nice thing. So we're really glad to be able to offer that. And it's also offering us the building blocks that we needed to implement the support for the removal of data nodes, which is going to appear in 22.3 if all goes well. Well, it's going to go well. We're pretty far along with the QD process for it. So despite my little introduction about gnomes and elves, we're not living in a fantasy world, so things go wrong, things break. And that's why you also need to have a solution or to make your cluster resilient. And in the case of sharding, we're leveraging our mirroring technology for that. Mirroring is proven by hundreds, if not thousands, of customers worldwide. So you can use it for high availability by using synchronous mirroring. And you can also use it for disaster recovery using asynchronous mirroring or even for reporting. So with the initial release, we only supported the synchronous mirroring, but now I think it's in 2020 something, we also introduced support for asynchronous mirroring. Also interesting for some of our customers, you don't have to configure everything up front before you enter the first record. You can still add or remove mirroring at a later time. So it's thrilling to talk to you about all the progress that we've made since that initial version when we really pioneered the concept. But it's also important to remain cognizant of what use cases sharding is built for. Sharding is built for analytical use cases, where you're doing a lot of query work or ingestion work that is data-centric and that involves large scans with lots of compute on the data. So that's where the parallelization that sharding offers is going to offer you the biggest advantages. That means that it's a great use case for analytics. It's a great use case it's a great fit for the data lakehouse, the data warehouse, or the data lake, whichever buzzword you fancy most. For archival, it's also a great fit. If you're looking for something where your transactional workload is distributed, it's not such a good fit because the way we implemented it does not allow for transactions across shards. So that means that not every application would suddenly be a good fit for sharding. But if you're interested, please come and see us, and we'd be happy to take a joint look at what your solution needs. So we're not done. We have a couple of things on the roadmap. I already mentioned removing the ability to remove data shards, which is pretty far along, and the ability to transparently convert a non-sharded table into a sharded one, and also vice versa in the case that you would need this. So there's still more of the operations side that we're aiming to be covering. I wanted to also talk about a couple of use cases, a couple of customers that are leveraging our horizontal scalability technology, and most specifically the sharding version. So the first one is Northwell Health. Tomorrow, there's going to be a dedicated session presented by Simon Shaw and Kyle Baxter from Northwell, who are going to talk you through their adventures, I should say, with rolling out sharding in 2018. They started with a pre-release version, and they've really implemented a nice distribution of their data warehouse, their clinical data warehouse, which is based on Health Insight. They were an early adopter, with a very creative team supporting it. So they drove several innovations and new features that we've implemented in the meantime, and it is still kind of a pilot architecture, but we're working with the HealthShare team, amongst others, based on the recent advancements that we've been implementing in the past 2 years, to really take the whole of Health Insight into a horizontally scalable version of it. And if you have questions about that, please come and see Ben or Matt or myself, and we'd be happy to talk to you more about that. But Northwell Health is really happy with this. They had initially exported data into a SQL Server instance, which was a big hassle, and then the query performance that they were getting out of SQL Server was not really satisfactory. They were seeing great parallelization across the shards and orders of magnitude performance improvements for their queries after moving into this sharded architecture. So a very nice use case with a very varied set of users. And if you're interested, come and see the session from Simon and Kyle tomorrow. Another use case is from a customer in financial services who is looking at a rather daunting data set with transaction histories, so financial transactions that spans over 60 terabytes for 7 years. And most of their queries will target the past year, but every now and but quite regularly, there's also queries that span like the past 2 years, or a time window that stretches across different years. So they were not in a position. So they have a very transaction-sensitive ingestion workflow, how the data goes into it. So sharding the whole thing was not really a practical option for them. But so after a transaction is logged into the system, it doesn't change. There's apparently there is the possibility that some of those records get amended, but that still is only in a period of 6 months or so. So what we're building with them is a topology in which the past year data is located on the main data server, and that the past history of that's more than a year old is in a sharded table that is presented through a logical union, and then those shards can use much more affordable hardware because they're only being touched by lower priority queries or at a lower rate than the recent history. So this is a nice and creative setup that is actually something that we were able to do because we started in 2018 with a really flexible set of building blocks for which later on we've provided kind of standardized topologies, but the building blocks are still out there and still available for those customer scenarios where where the scenario requires a little more flexibility. And then another capability that is that we've worked on is for Federated Tables. So this is a customer that has over 100 different instances of almost the same schema. So they have small data warehouse deployment, or small. These also go into the terabytes. They have 100 different instances of that database for different sites, so different healthcare facilities, and they want to be able to analyze the aggregated data across them. But there is no real opportunity to, or they don't wish it. Those are already data warehouses, so they don't want to put it. They don't want to copy the data into yet another data warehouse and duplicate the data that's being stored. So, and those instances will still be managing the data all by themselves. So this goes back to how what I was explaining about sharding earlier. So sharding takes care of managing the data and querying the data. So this was a very interesting use case from a customer that was interested in being able to query data that's distributed across nodes, but not interested in the managing of the data because that was still taken care of at the individual instance level. So that's why we implemented read-only federated tables, where we'll be deploying a sharded cluster in sort of an overlay of their existing infrastructure and offer them a way so that they can issue queries across the whole logical union of all those different databases. So we've got the technologies ready. We've got a prototype that we tested in-house, and we'll very shortly be deploying that on the customer environment in a test environment with a handful of sites. So those are three very different examples of customers who we are working with. The first one is live. The second one is close, and this is kind of a pilot project where the flexibility of the IRIS data platform is key to kind of offering a horizontally scalable solution that fits exactly the customer needs and is not just some standard cookie cutter style solution. So with that, I want to thank you for attending this session. So this was kind of a story to get you going on horizontal scalability. We'll have a lot more to talk about tomorrow, when during the keynote we'll also be talking a little more about some of the recent advances in SQL that are also oriented at the really large data sets and how we can improve performance for those. In case you have any questions, please feel free. We've got about 10 minutes left. Please.
You talked about the compute and scaling for the compute horizontally.
Mm-hmm.
And you talk about adding and removing compute units. Can it be done in an automated way, or is it really manual?
I'll repeat the question for the sake of the recording. So the question is whether the scaling is automatic or requires manual work. That is an excellent question, and it is. So right now it is configuration or API driven, which means that you can script it. So we've got customers who scripted it, and most interestingly, I think it's I'm not sure if it's part of what Renan showed. Well, it's not part of the health share demo that Renan showed, but that platform with that really nice canvas is in there. That's all based on Kubernetes, and in Kubernetes we're kind of tapping into the features that Kubernetes offers for auto-scaling to also script the provisioning of another InterSystems IRIS node. But as you know, InterSystems IRIS is a data platform. It's not a provisioning platform. So you need to make sure that your script understands the provisioning infrastructure that you have available to make the infrastructure available on which you can then deploy InterSystems IRIS. So those auto-scaling capabilities. They would be Kubernetes scripts that know how to handle IRIS and Kubernetes. So that's a long-winded way of saying, yes, we've got examples of scripts where we can do it, but it's not kind of an out-of-the-box feature of IRIS itself. But it's a great feature of the smart data services concept that Jeff will be talking about in his keynote tomorrow, and Scott as well. Sorry, you also had a...
Maybe we talk about the mirroring scalability, right?
I kept thinking about the cap theorem. You know how the InterSystems IRIS addressed this issue? The consistency, availability, and partition tolerance problem.
Oh, the cap theorem.
Yeah.
That's a great question. Luckily, Tom is here for the hard ones. So are we a CP or an AP? CP. Thank you, Tom. So the cap theorem is a kind of challenge is not the right word, but it's kind of a theory that a high availability solution cannot at the same time offer full consistency guarantees, full availability guarantees, and full partitioning safety. So if the shit hits the fan and there's something and a machine dies, either of these three capabilities must be given up. So our mirroring technology offers you safety for consistency and against partitioning your cluster, but at the expense of the availability thing. But there's sometimes some interesting debates to be had. Maybe we can do that after the main session.
Hi. I have a question regarding first of all, Epic is using their on cloud, on-prem.
Epic is increasingly offering its customers the ability to deploy in the cloud through a managed offering from Epic itself. But
Okay.
maybe that's a question.
Actually, we have a database which is larger than 6 terabyte, with around 1 billion records in the main table. And what is the relationship between the mirroring to the sharding? I mean, can we do sharding on async read-only mirror members?
You can have async reporting mirror members. So the way how sharding and mirroring work together is that you're deploying your sharded cluster as a cluster of IRIS instances, and those, rather than plain single instances, those instances can also be mirror sets, I should say. So your mirror sets could be synchronous mirror sets or asynchronous mirror sets or async reporting mirror sets. So I don't have a diagram at hand.
Is there any change in the mirroring architecture in a way that today you can have a sync mirror only with 2 failover members?
No.
It's something that is still true, right?
That still holds, I think. Yes.
All right. Another question is, any class can be transferred to a sharded table?
There are still a number of features. Some of those are kind of legacy features, such as the object synchronization feature, and there are also, if you're using custom storage, for which we do not support sharding. But many of the limitations have been, or many of the limitations that were there in 2018 have been lifted. So you can have.
And last one, how do you address the thing that if you want to be elastic, then let's say we have a million rows table, and we have like let's say we divide them to 4 data instances. So each of those will get 250,000. Now, you're elastic, you add the 5th one. So actually, at the end of this process, each of them would have 200,000. But when you want to reduce, you have to take the data that is physically on the 5th node to be able to get back to the other 4. So this is something that the system is doing automatically.
This is something that is coming in 22.3. So you tell the system, I want to dispose of this shard, and then it will start offloading the data from there while your operations keep running. And as soon as it's done offloading that shard, it will disconnect it from the system, and you end up with your 4-node shard again, 4-node cluster again.
All the other things that are related to sharding or to split data between different nodes, like locking mechanisms or proper handling of indices, are being dealt also?
Indices are partitioned along with your data. So that is indeed very important. So that's very different from how global mappings would have worked. And I think I'll after I switch off the microphone, I would love to talk to you about table partitioning, which is something that we'll be working on shortly. But and
thank you.
So if you also had a thing that's definitely worth talking about. So we're asking about locking. So under the hood with sharding, what we do is we will distribute the data for sharded tables across the different nodes, but you can also leave some of your tables unsharded. So for example, small lookup tables, there's no point in sharding them, which is that overhead. So you keep them, they will stay on either the shard master if you have a dedicated system, or on the first shard. If your application logic wants to take locks, those locks will be taken on the shard master database, where the non-sharded data is, unless you take it to, or unless you map, or unless you take a lock to the specific global prefix that is mapped locally, and then it can be a shard local lock. But if you take a lock on a record, we take care of that automatically. So we figure out if it's sharded or not sharded, and we'll
it's an ECP lock.
Sorry?
ECP lock.
Yes.
Probably. Thanks.
So I'm
Great
from
questions.
Northwell.
Yes.
I'm from Northwell.
Thank you.
And I worked on that SQL server a little bit, so I'd like to talk to you about that afterwards, give you a little more details about that. You know, but you're not inaccurate, but I'll give you a background on it. Okay, also, his question, he said that you could have a sync members, and you can't have async members. You can't have additional, like DR and read-only systems.
Yeah, you can have all of them. All of
But
them
I thought you
together.
told him no. But
No, you can't have two synchronous members.
right, you have your primary and backup.
Yeah, but
right,
you can't have
and
a
then you
second
could
member.
add async members off of that, right?
Async, yes, but you can't have two sync backup members.
Oh, yeah, that's not, okay, right. You can't do that with mirroring, right?
Hmm.
Yeah. It's nothing to do with chart, or, with
No, no, indeed. Yeah, we're just consumers of
Yeah.
mirroring.
All right. Anybody? Oh, there you are.
Well, in that case, thank you all. Thanks for the great questions.